Hello everyone, welcome back to the channel. I'm Evan, co-founder of Hello Interview and a former Meta staff engineer. And today I actually wanted to take a step back and make a more beginner-friendly video for you all today. So many of you have seen our system design video breakdowns. We're going to do a new one of those today, and it's going to be for the classic question, design a URL shortener, which is everybody's first system design question. And in this video, as I mentioned, I'm going to slow things down a bit. I'm going to teach concepts that we otherwise take for granted in some of our other videos. So if you're new to system design or you're dusting off the cobwebs, this is the place to start. If you like our content, you want more of it, please make sure that you like and subscribe. The increasing number of subscribers is really motivating to us. It makes us want to create more content for you. So make sure you smash those buttons if you haven't already. Lastly, if videos aren't your thing, I've linked the written resources in the description as well. So if you don't want to watch this whole video, you can just come here and read the written form. There's also tons of other common problem breakdowns, over a dozen now on the left-hand side. You can also try all of these yourself with guided practice. And so guided practice is a tool that quickly just lets you walk through designing systems on your own. And then you get this personalized feedback for each step along the process. This feedback was tuned by myself and my co-founder, Stefan. So give that a go. And then the last thing here is that if you're looking or if you're preparing for interviews, the best thing that you can do is mock interviews. And that's our specialty here at Hello Interview. So come on over, do a mock interview with a senior plus engineer or manager from your target company, and they'll tell you exactly where your gaps are and how you can improve. All right, let's get into it. Before we start designing our URL shortener, let me take a brief moment to just explain the framework or the steps that we're going to follow both in this interview. And this is also the framework or steps that I suggest you follow for any of your system design interviews. So the first thing that we're going to do is we're going to define the requirements of our system. This is both the functional requirements or the core features, as well as the non-functional requirements or the qualities of the system. Things like scale, durability, fault tolerance. After we do that, we'll define or outline the core entities. This is really simple, high-level list of the core entities that are going to be persisted and exchanged in our system. Another way to think of this is like the names of the tables or collections that you would have in your data model. Once we do that, we're going to move on to the API. This is the user-facing API. It's the contract between your client and your users and your backend service. From here, we're going to skip data flow. This is only applicable to infra-heavy system design questions. So like design a rate limiter, design a message queue, stuff like that. So not applicable to a user-facing product like a URL shortener. So instead, we're going to go right to high-level design. This is where we're going to head to the whiteboard. We're going to start drawing boxes and arrows in order to outline a system where the primary goal is to satisfy the functional requirements that we outlined in one. And so at this point, our system is going to be really simple. It's not going to be able to scale. It's not going to be able to do anything too fancy. It's just going to be able to satisfy those core features that we outlined. But from there, we're going to move on to our deep dives, where things are going to get fun, and we're going to go one by one through those non-functional requirements in order to evolve our high-level design in a way such that it ends up satisfying each of those non-functional requirements. And at the end, we're going to have a system that satisfies all of our functional requirements and all of our non-functional requirements, and we're going to feel really good like we passed the interview. As promised, we're going to start our design with the requirements of the system. And so the first thing that we do is we start with the functional requirements. The functional requirements are the core features of the system. This is where you're going to try to identify the top 2 to 3 features that are necessary and that you will have time to design in your 35 to 45 minute interview. Now, if you were told to design a system that you already know well, then this should be pretty easy. But you might also be asked to design a system that you've maybe never heard of. In this case, you're going to want to ask a lot of questions. This is the time where you would pepper your interviewer with questions in order to better understand the system that you're required to build. In our case, what is a URL shortener? Well, a URL shortener is a service that converts long URLs into short ones, and then those short URLs will redirect you to the original URL. So you can take this long URL, give it to the URL shortener, it returns this short thing, you can put the short thing in your browser, and it's going to redirect you here. Pretty simple. So in our case, functional requirements can always be thought of as like these users should be able to, users can, users will statements. And so what are ours? Well, that first one is that users can create a short URL from a long URL or an original URL. Perfect, that's our first thing. What's the second thing? Well, users can be redirected to the original URL from the short URL. Easy, right? Those are the two core features of a URL shortener. Now, I'm going to add a little bit of flavor that's often added in these questions, and then I'll have candidates address if I'm conducting this interview. And that's that I want to optionally support a custom alias. And so this is that users could come to us with their own short alias. Maybe instead of us generating this random thing, they give us, for example, Evan, and then their short URL becomes /Evan, assuming it doesn't already exist. So we'll support that, optionally if they want to provide it. We'll also optionally support an expiration time. And so maybe somebody's creating a short URL for a conference or something, and they only want it to be valid for the week, then we'll expire it after that week if they give us that expiration time. This means that if somebody tries to navigate to that short URL after the expiration, they'll just get an error or something telling them that it's already expired. So these are the core functional requirements of the system. The next thing that you would do is that you would go into the non-functional, what we refer to as the non-functional requirements of the system. Now, the non-functional requirements are, instead of being features, and they are the qualities of the system. And so the quality of the system are all of those words you've heard. These are like these illies, these illities words, these things like the scalability, the latency, the durability, security, fault tolerance. Is your system compliant? This is where you talk about CAP theorem. All of those things. What qualities does the system need to uphold in order to ensure a good user experience and that we're meeting user expectations? And so what you typically want to do when you get to non-functional requirements, and these are hard oftentimes, especially for more junior candidates to think of, is that you should go one by one through those ILLI statements. Maybe you have a list of them kind of readily on your table as you're going into the interview. And you think about which one of them are uniquely interesting and relevant to this system. And so, for example, the first one that we could look at is latency. How is latency important in our system? Well, it's really important that that redirection is low latency. And so one system requirement, and these are, instead of users should be able to, this is the system should be statements. So the system should be low latency on redirects. So if we give it a short URL, we should automatically go to that original URL. So not only did we choose the non-functional requirement, but we put it in the context of our system. It's not just low latency, it's specifically low latency on redirects. And we want to quantify it too. We're going to say about 200 milliseconds. 200 milliseconds is a good number here because it's what is the humans perceive as real time. So anything under 200 milliseconds, you wouldn't even notice the difference. 200 milliseconds is like the snap of a finger. It's real time, so it's a good lower bound for us here. So we have one non-functional requirement, low latency on redirects. Another thing that we can think about is the scale of the system. And this is a time when I would ask my interviewer. I would say, how large of a system are we designing? How many users? What's the scale of this system? And they might tell you to estimate it, or they might just give you kind of a sense of what the scale is. I typically would do the latter. And I would tell a candidate that they should expect 100 million daily active users and around 1 billion URLs that gets shortened kind of in totality over all time. And so that would turn into a functional requirement of the system should be able to scale to support 100 million daily active users and 1 billion URLs. Fantastic. Making good progress on the non-functional requirements. Another one that's interesting here, which is a little bit hand-wavy whether it fits in non-functional requirements, but I want to call it out because of how important it is. It's that each of these short URLs or each of these short codes, they need to be unique. So the system needs to ensure uniqueness of short codes. These short codes are these kind of things that we're appending to the end of the URL, right? We need to ensure uniqueness of short codes so that there's no collisions, so that people don't end up getting redirected to a site they weren't expecting to go to. So those always need to be unique. That's definitely going to be a core system requirement. And then the last one here that I'm going to do, which typically you might do first, but it's always going to be considered, and that's CAP theorem. So really quickly, what is CAP theorem? Well, CAP theorem is a theorem that states that when considering consistency, availability, and partition tolerance, you can only ever have two of those three things. Now, partition tolerance in distributed systems, like we're almost always designing in system design interviews, this is a guarantee. You have to have partition tolerance because you're going to have partitions. You're going to have different instances, for example, of your database. You're going to horizontally scale your servers. And so the decision really becomes, is it consistency or availability? Does my system need strong consistency, or does my system need high availability? And what I want you to think about as you're in an interview is, do I need strong read after write consistency? The way to think about this is, does every single read of my system have to read the latest write, or else the system breaks or fails in some way? So common examples of systems that need this read after write strong consistency are like a banking application or a ticket booking system. The example being, in the ticket booking system case, if somebody went and booked the last ticket to the Taylor Swift concert in Germany, and then I in America went to book that same ticket, and I went and read the database and it told me it was still available because I didn't have strong read after write consistency, I would book that ticket and now we would both show up and we would be fighting for the same seat. That would be bad. This would be like a fatal error to our system. We can't have that. Same too in a banking app. If somebody else trades a stock, especially if it's a low float, no matter where I am in the world, need to know that that stock was traded because it might impact the price before I buy or sell respectively, right? In the case of a URL shortener, do we need that strong read after write consistency? Well, you can imagine that somebody gives us a long URL, we shorten it, we give them the short URL back. Does anybody who then hits that short URL immediately need to be able to be redirected? We could say no. And the reason we could say no is because, first of all, there's some time that it takes for a user to share a short URL with other users and for it to start being used, and that gives us time to be eventually consistent. If for some reason somebody was wicked quick, A, there are ways that we can handle that by making sure they're redirected to that same original node. But B, if they didn't get redirected in that first couple seconds, up to even a minute, who cares, right? Like, we can show them a little error that just says, like, we're still saving this in the system. Try again in a minute. And no big deal. The world wouldn't end. Two people wouldn't show up to the Taylor Swift show fighting for the same seat, right? So because that's the case, because we don't need strong consistency, we're instead going to go for availability. And so we're going to say high availability. And so we don't need strong consistency. Wow, I don't know how to spell that. We don't need strong consistency. Instead, we can handle eventual consistency. So eventual consistency for URL shortening, right? Cool. Okay. So that's our non-functional requirements. The last thing that I'm going to say here is that many guides will instruct you at this point into go into back of the envelope estimations. So you'd come in here, you do back of the envelope estimations. You would end up talking about things like scale estimations, latency estimations, like total storage estimations, whatever. This is fine. You can do it, but I'm going to suggest that it's useless. Estimations and calculations while doing system design is very important. But doing it up front like this, I find, as an interviewer, is almost always useless. Candidates will do some basic math about storage, latency, etc., and then they'll look at me and they'll go, okay, yeah, so it's going to be a big distributed system. And it's like, yeah, we kind of knew that already, didn't we? There was 100 million daily active users and a billion URLs. You're not telling me anything new. And you're not going to change your design based on that information. You are always going to do a distributed system. And so what I argue is that doing math for the sake of doing math is not useful. Instead, you should tell your interviewer, I'd rather not do math up front, and I'm going to do it during my high-level design or my deep dives if I need it to make a decision. And so the key here is that you're going to do calculations when the result of those calculations will directly inform a direction or a decision that you're going to take in your design. And doing it up front like this, in my experience, does not satisfy that. Next up, we go into the core entities of the system. Now, the core entities, as I mentioned, these can be thought of as basically the tables that you're going to have in your database. This is the entities that your system is persisting, storing in the database, and exchanging via the APIs, right? And so core entities, as we suggest at Hello Interview, you start by just listing off these entities. Don't worry about the full data model yet. You're going to get into that later. I would communicate this proactively with your interviewer. I would say, I'm not going to do the full data model just yet. Instead, I'm going to list off these core entities, and then as I get into my high-level design, I'll be more explicit about the fields or columns for each of them. But in our case, what do we know that we have? Well, we have an original URL, we have a short URL, and then we have a user who creates them. These are the entities in our system. Pretty straightforward. And the reality is that this system is so simple that you could outline the data model here if you wanted to. You probably know it at this point. The reason that we don't yet is because for more complicated systems, it's oftentimes too early, and we haven't had a chance to think through our API and all of the requirements that would have us understand what the full data model would be. But in this case, it might be fine. I'm going to go with this, and this is a good enough core entities for now, which takes us then to our API. The API is where, again, we define that contract between our client or our users and our system. And the way that I suggest you go after the API is very methodically. You're just going to come up here to your functional requirements. And in most cases, it's a one-to-one mapping between a functional requirement and an API. Not always. Sometimes you have like 2 or 3 API endpoints for each requirement, or maybe you don't even have an API endpoint for a requirement. But you should come up to this list and you should say, the first thing I need to do is users should be able to create a short URL from a long URL. Okay, let me make sure that I have an API that supports that. So in doing so, the first API that we need is to be able to shorten a URL. And so this can be a post endpoint to some URLs resource, and it's going to return a short URL. We're just going to reference here our core entity. Right? It's going to return a short URL. And the body here is going to be what? Namely, it'll have that original URL, again, referencing that core entity. It could have that optional custom alias. I'm going to use question mark in order to indicate the optionality there. And then we can also have optionally that expiration time. So that expiration time, right? And so there's our first URL, our first API endpoint, which is going to allow us to take an original URL and return a short URL. When you're doing these system design interviews, you oftentimes will use REST APIs, though not always. When you are using REST APIs, a couple things to think about. You want to make sure that you get your verb correct here. You have post, put, patch, get, delete, etc. Most often, you're just going to use post when you're creating a new resource, put or patch when you're updating a resource, delete, of course, if you're deleting a resource, and then get if you are, quite obviously, getting or fetching a resource. So make sure you have those down. And then when it comes to these paths, you typically are going for a plural noun. And so to be honest with you as an interviewer, I don't care about all of this. I think this is like kind of silly semantics that are easy to change, figure out. They're not the most interesting part of any design. But especially at the lower levels, you'll have like what I'll call RESTful API zealots, interviewers who really care about this. And so I just want you to be aware and considering things appropriately. Okay, so that's that first API endpoint, right? We just satisfied that first functional requirement. The second one is users should be able to be redirected to the original URL from the short code. Okay, so we need to handle an API endpoint for redirection. And so how is this going to work? Well, we're going to have some get endpoint, and it's going to go to / like our short code, or to use our core entities, it's just going to go to our short URL, and then it's going to return a redirect to our original URL, right? So that's pretty straightforward. Now, in case this isn't obvious, the way that these systems work, of course, is that when you run this get, and we'll get into this in a moment, when you run this get, you're hitting our server, the server that we own, our URL shortener, with that short URL and that short code. And then we can take that code, figure out what we need to do with it. We'll get into that later, and then issue the redirection. But that's how this ends up working. So here are our API endpoints. Super simple. We double check. We have an API endpoint for each of our functional requirements. These fully satisfy those requirements. We feel like we're in a good spot, and we're ready to move on to the next section. So at this point, we've done all the setup work. We have a really clear understanding of the system that we need to design. We know the core entities that are persisted and exchanged, and we've defined our contract with our backend between our client and our server. And so the next step is to come over here and do our high-level design. This is where things are more fun. We get to go to the whiteboard, we get to draw, and our primary goal, again, is to just satisfy these core functional requirements. So we're not going to worry about scale or meeting latency or ensuring uniqueness or availability or any of these things yet. We're going to do that later. We're just going to get a simple design down that works. And by following this framework, our mind is just working linearly, so that even if we're given a problem that we haven't seen before, we can just build the design up step by step by step. Okay, so when it comes to the high-level design, here's how I recommend you do it. You come over to each of the APIs, and you start with the API, and you draw out the system that's necessary in order to satisfy that API. This is equivalent to going step by step through each of the functional requirements as your node. But by doing it for the APIs, you can be really clear about the data flow and about what needs to be the input and the output of each request and how the system kind of transforms those appropriately, if you will. So let's come over here and let's draw this out. I'm going to start simple, and I have a given client. This client here is just maybe like the website, right? Pretty simple. And then I also have a primary server. So this is going to be the primary compute resource in my backend. And then I'm also going to add a database. I'm going to add a database. And so this is a very classic design pattern, just a client-server database relationship. The client is going to make a request to your backend server. Your backend server or your server is going to do something, persist it in your database, and then return it back to a client. And so in our case, what we're considering right now is what happens when a user tries to shorten a URL. They're going to make a post request to /URLs, and then we're going to return to them a short URL. Well, how are we going to do that? We're going to do that because they're going to make that API request here. That API request is going to be, get short URL. It's going to hit our primary server. Our primary server is going to have some magic black box that creates short URL. We'll talk about how it does that later. We'll stay abstract for now. So it's going to generate that short code, and then it's going to come over here and it's going to save it to the database. I'll make that a two-way arrow. This one should be two. Cool. So it's going to come over here, it's going to save it to our database, and then return it back to the client. Well, what is it saving to our database? Well, we probably now define some data models. Instead of having separate entities or separate tables for the short URL and the long URL, which we could do, I'm instead going to combine them in this case into one because of how simple it is, and this is going to make more sense. So I'm going to have a URL table, and this URL table is going to have the short URL, and it's going to have the long or original URL. It's probably going to have the creation time and the user ID, a forwarding key to the user that ended up creating this. And then subsequently, I'm going to have a user with a user ID. I'm not going to outline anything more. Of course, a user table will have an email, a password hash, salt, all of these different things. Who cares? I see so many candidates get distracted by those things in an interview. We're focused on the core functionality here. All of that is auxiliary. And so maybe I just do this. Of course, all the additional metadata. Cool. And so we take a look at that first API endpoint that we had, post to URLs, return a short URL. Here's how it's going to work. The client is going to post to our primary server. It'll create a short URL. It'll store that in the database as a mapping between the short, the long URL, the creation time, and with the user ID, and it'll return that short URL back to the client. Easy. We got it. First one down. Now the second one is that the user needs to get that short URL and be redirected to the original URL. And so how are we going to do that? Well, now we have an additional thing here. We have this redirect, which takes in the short. This one took in the long. And so that's going to come from our client. It's going to hit our primary server. Our primary server is going to look up long from short, right? So it's going to go over to our database. It's going to query it based on that short URL. I'm probably going to want to make that our primary key. It's going to query based on the short URL, and then it's going to return the long URL back to the user. And it's going to return this back to the user with, importantly, a 302 redirect. And so a 302 redirect is just the HTTP status code, which tells the browser, I want you to take this URL and automatically navigate to it. I want you to automatically navigate to this URL. And when it comes to redirects, we have two options. We have a 302 redirect and we have a 301 redirect. These are both different HTTPS status codes. And so in the case of a 301 redirect, this is a permanent redirect. And what it basically means is that your clients, your browser, DNS servers potentially, they can cache this redirect. And in the future, they might not even need to go to your service. They're just going to redirect it immediately based on the cache. In the 302 case, this is temporary. And so it's never going to be cached. They're always going to come to us first. We're going to look it up, and then we're going to send it back. And so there's a conversation that you would have with your interviewer at this point, potentially about whether 302 or 301 makes more sense. Now, it depends on your requirements. I suppose in our case, we don't care about analytics, which is what would make the 302 the right answer here. Because in the case where you have analytics, you can show users how often their short URL is being queried. You would want to make sure that it always comes to your server, because then you can log and you have an understanding that this redirect was requested. In the 301 case, you're not going to get that, you're not going to be afforded that ability. It's not going to hit your server, so you're not going to be able to log anything for future analytics. Now, this permanent redirect would be better if we were worried about compute cost, if we were worried potentially about not having to scale this server in the future. Then by having it be permanent, it's handled by caches elsewhere and may never even hit our backend service in the first place. That's pretty nice. And so there's pros and cons here. Typically speaking, you want to go with the 302, even the cost to how many servers you may need, because it allows you to understand if things are working. Even if you're not showing users analytics, even if that's not a core requirement, you would be tracking that internally as a platform, as a product. And if you saw things drop off a cliff there, well, you would know something broke, probably broke on the client, and we're not getting these requests anymore. And so by making it a 301, you lose that visibility. And this is the argument that I would make in an interview and why I would decide on a 302 redirect here. And so the server will respond with a 302 redirect with the original URL, and the client will then navigate to that original URL and they'll be viewing that original website. Awesome. So super simple. We went through each of our APIs. We now have a really high level design that satisfies both of our core functional requirements. I suppose with that being said, as I just went back here and checked, as you should do too, I noted that we actually didn't discuss two parts of that functional requirement. That's the custom alias and the expiration. So let me come back and amend appropriately. We're going to add here, that short URL / custom alias. This could be either of those things if they provided a custom alias. And then we're also going to add that optional expiration time. So an expiration time here. And so now what a user would do if they gave us a short, if they wanted to get a short URL and they gave us a long URL and then they also gave us a custom alias, we would need to first look up in the database, does that custom alias already exist? If no, add a new row where the short URL is the custom alias and return that back to the user. Easy. And then in the case of expiration time being provided, we'll make sure that we add it here. And then on the redirect call, when we come to look up our long URL based on the short URL, we'll also check the expiration time. Is the current time greater than the expiration time? If so, return an error instead of a 302 redirect. Okay. With that being said, now we have a high-level design that satisfies each of our functional requirements, and it's time to go deep in order to expand this design to support each of our non-functional requirements. So as we move on to the deep dives, we're going to come over to our non-functional requirements, and we're just going to go one by one through them, evolving this simple high-level design such that it meets each of these non-functional requirements as well as the functional requirements that it already satisfies. And now, if you all will allow me, I'm actually going to take some liberties here, and I'm going to start off with the third one, ensure uniqueness of shortcodes. And the reason I'm going to start off with that one is because you'll realize that in our high-level design, we intentionally overlooked kind of the core of this problem. We black boxed this create a short URL. That's the hard part. That's the interesting part of a URL shortener, and we just hand-waved it. Now, we did that intentionally. The reason we did it intentionally is that a common mistake I see candidates make is that they go too deep on any given part of the design too early. And then all of a sudden time runs out, and they didn't even get a chance to satisfy all of the functional requirements, the features of their system. This is a mistake. And so you want to remain pretty high level, make sure that you have the base down, make sure you satisfy those functional requirements, and then come back and go deeper. And that's exactly what we're doing here. So I would have told my interviewer, I would have said to my interviewer, I'm black boxing this for now, but I'm going to come back to it. And now let's do exactly that. So what do we need? We need two things when it comes to creating a short URL. Well, maybe we need a couple of things. We need the creation to be fast. That's reasonable. We need it to be unique, and we need it to be short. Those are the three things that we care about. How short? Well, we could ask our interviewer, or we could guess, but typically we're talking in like this 5 to 7-ish character range, right? So 5 to 7 characters, maybe, is short enough. And so let's talk about some options that we have here. In an interview, you do exactly this. You kind of work your way up, building from the most simple solution to something more complex, certainly if time allows. So the first thing that we could do is that we could just take a prefix of the long URL or the input URL. So any given long URL that comes in, let's just chop off the first 5 to 7 characters, stick that then as our short URL or our short alias, or our short code, and then append that to the end of our www.bit.ly.com/that prefix, right? Now this is obviously bad. Why is it obviously bad? Well, because there are tons of URLs that share the same prefix. What about every single URL at www.twitter.com or www.facebook.com or any of these different common URLs? They're all going to share the same prefix. And now we don't have a one-to-one mapping between short and long URL. We have a one-to-many mapping. And this means that if you give us one of those prefixed short URLs, we have no idea which one of the thousands, hundreds of thousands of long URLs it actually maps to. So it's a terrible idea. Don't do it. The second thing that we could do is we could use a random number generator. This is a much better idea. So this is a random number generator. And so we ask ourselves, like, how large can this number be? How large should this number be? How large would this number need to be? Well, if we come back over here, we're reminded of our scale that we're going to have 1 billion URLs. And so this means that this random number needs to be at least between 1 and 1 billion. Of course, if it's just between 1 and 1 billion, our collision rate's going to be really high, so we might want it to be higher than that, but it needs to be at least that. 1 billion is 10 to the 9, or 10 characters. Right? 10 characters. That's more than our 5 to 7. That's too many characters. And so we'll need to do something a little bit more sophisticated in order to compact that. We can't just append 10 characters to the end of this thing. And we need at least 10, remember? We probably need 11, 12, 13 in order to make sure our collision rate is lower. But here's what we can do. We can do something called base 62 encoding. And so base 62 encoding is basically can be thought of like a numbering system, like 0 all the way to 1, 2, 3, 4, 5, 6, 7, 8, and all the way up. But instead, we're going to incorporate the alphabet. And so the way that the numbering works is that we go from 0 to 9, and then we go from A to Z, and then we go from A to Z lowercase. And so what this means is that 10 is actually A, 11 is actually uppercase B. And it means that any given character can now encode 62 options as opposed to just 9 or 10 like in the traditional base 10 encoding, right? So we can take a large number and then base 62 encode it. And so now how large would we want this to be? Well, if we had, for example, a code that was length 6, let's go right between our 5 and our 7, then it would be 62 to the 6 possible combinations. 62 to the 6 is 56 billion, about. And so that's pretty good. We have like a decent amount of space there. We can randomly choose a number between 0 and 56 billion. We can base 62 encode it, and it's going to be a short code. It'll be of length 6 in base 62 encoding. But what about our chance of collision? What is the chance that a random number between 0 and 56 billion, when calculated 1 billion times, ends up colliding? Well, you might be surprised by this, but the collision probability is actually really high. This is oftentimes referred to as something called the birthday paradox. I'll write that down in case anybody's interested in reading about it. So this is the birthday paradox, and it's this counterintuitive probability problem that states that there's actually a 50% chance that 2 people in a group of only 23 people have the same birthday. I'll say that again. You can see why that's so counterintuitive. If you have 23 people in a room, there's a greater than 50% chance that at least 2 of them share a birthday, despite there being 365 days in a year. Now, the formula that is used to calculate that can be used to calculate the probability of a collision on 56 billion randomly generated things as well. And you wouldn't need to know this in a system design interview, but just because I thought it was interesting, I went about and I did this. And it turns out that out of 1 billion random generations, there's an estimated 880K collisions that would happen here. So that's a lot. That's like a decent number of collisions, right? It's depending on how you define a lot. 880K over 1 billion might not be that many, but it's certainly a large enough number that we would end up with more than a one-to-one mapping. And so how do we address this? Well, one thing that we can certainly do is that we can take this approach. We can random number generator, base 62 encode. Yes, there might be a collision, but what we'll do is before saving it to the database, we'll come over to our database and we'll read the short URL, see if any exists like this already, and only if they don't exist, write to it, update it. So we just introduced another read. Instead of calculate the short URL and save to the database, it's calculate the short URL, check, and then save to the database, right? So that's totally possible. So basically we just need to check for collision first. Is that a big deal? Not really. It's an extra read. There's some consequences to that, but no, it's not a big deal. That's one option. Another option is that we could hash the long URL. This is a common one that I see a lot online and that candidates often raise. So they can take that long URL and they can call some hash function. And so maybe that hash function is like MD5, something cheaper like Murmur hash, something like SHA-256, cryptographically secure, whatever. But you get a long URL, and then you would end up getting some output, right? Some hash, and you would take that hash and you would base 62 encode that hash again, right? And then you would slice it to take just those first 6 characters. So that would be the operation that you would do there. Now what you end up with is 6 characters of base 62 encoded. So you end up with the same thing that we ended up with the random number generator. And because of how hash functions work, right? A hash function, despite it being deterministic, has that waterfall effect such that if you change just one bit on the input, the whole hash should change significantly, basically increasing the randomness of the hash that's generated. And that property means that the output is actually just exactly the same as the random number generator. It is literally the same thing. There's 56 billion possible combinations. The chance of collision is exactly the same. So same as above. Again, this would totally work. It would work exactly the same. We just need to make sure that we check the database first. Can we avoid checking the database is the question. The answer is yes. Is it a better approach? The answer is maybe yes. But what we could do is we could use a counter. Like, why introduce this randomness in the first place? Why doesn't the first person who comes to us just have short code 1, the second person have short code 2, the third person have short code 3, and so on? And so we can just have incrementing a counter. We can just increment a counter for each new short URL or each new long URL that needs to be turned into a short code. And then again, we'll base 62 encoder. We'll always do that so we can kind of make this space more compact. And so this allows us to get up to that 56 billion with 6 things, but we're guaranteed to never have a collision because we're always just linearly increasing. There's a sequential nature to it, right? We're going to go 0 all the way to 9, and then to capital A, and then to capital B, all the way through until, eventually we have 6 characters of that base 62 encoding. And so this is great. And maybe what we can do here just to visualize this is I'm going to expand this guy up like this, and we can add in here like some counter. So there's some counter in here, which we're just always going to go grab the next count. What's next? Right? Grabbing a count is fast. It guarantees that it's unique, and by base 62 encoding it, we guarantee that it's short. It's not without its flaws, though. So there's a predictability, which is bad for security. And so what this basically means is that anyone who wants to know our short URLs can. They can easily know how to count, and they can easily know how to base 62 encode. And so not only could our competitors know how many URLs we've shortened by just continuing to call our service until they end up not getting a short URL that converts to a long URL anymore, but they also can just scrape all of the long URLs that we have, right? By just calling the short URL with that new incremented code each time. And so maybe this is a problem, maybe it's not. This is a product decision. We could say when users go to create a short URL, like a warning, these are not, don't shorten private URLs, right? We're not responsible for this. That's one option there. We can of course have rate limiting so that our competitors can't just come and scrape and grab all of these URLs if they want to. But we also could do something more sophisticated, and that's just not let this become a problem in the first place by introducing something that's oftentimes called a bijective function. And so you don't need to know this again in a system design interview. I think this is just interesting. If you brought out these facts, they'd probably be impressed, but you don't need to know this. Bijective functions are functions that just issue a one-to-one mapping. And so there are libraries. One of the most popular ones is squids.org. You can look that up if you're interested. And it takes a number, and then it returns to you a hash that looks exactly, or a base 62 encoded string that looks exactly like the short URLs you see on Bitly. And it can take that number that you provided it and then one-to-one map it via some obfuscation so that you can no longer incrementally know how to get the next URL if you're a competitor or a hacker or anything like this. So these bijective functions exist. It's worth you looking up on your own. I'm not going to go into more detail, but that's one option there. Now, the nice thing about this counter approach, of course, is that we don't need to do the read, right? We know that every single one of these is unique. So now we get the counter, we run our bijective function if we want to, and then we go store that shortcode in the shortcode in the URL table, and we're good to go. The last thing that I'll say here is that you're probably thinking to yourself, oh no, this isn't great. Why do you have a counter on a single server? You're right. We'll talk about it when we get to scale. But for now, here are your options in order to create a shortcode. Both 2 and 3 are totally realistic, and you could provide these in an interview, and it should totally be passing. You'll just need to call out the need for that collision check. 4 is an option I think that I like in this case because it doesn't require that additional check. But ultimately, there's very small differences between them. Let's come back over and look at what non-functional requirement we should go into next. So I'm going to go back in order now, and I'm going to jump into low latency on redirects. And so how can we make this redirect as low latency as possible? Right now, what is it that we have to do? Well, the client has to make a request to the primary server. The primary server needs to look up that short URL in our URL table, return the long URL, and then that long URL needs to be returned to the client. Now, the expensive part of all of this is this database lookup. That's what's going to take the most time. And now, without any indexing, and I'll explain indexing here in a moment, but we would have 1 billion rows here. And you would need to look at every single one of these rows and try to find the short URL that you're interested in so that you could return the long URL that it maps to. That would obviously be like prohibitively expensive. It would take a really long time to do. And so the common thing that we do in databases in order to make these queries and these lookups more efficient is that we use something called indexing. And so each URL table, you can define a primary key. This is true of most database systems. Now this primary key does a couple things. One, it enforces uniqueness, which is good in our case, certainly. But it also ensures that an index is automatically built on that column, right, on that primary key in the table. And this index is typically kept in memory, not always, but you can think of it as this thing that's kept in memory that is a pointer to a location in disk. And so instead of us having to go to disk and seek and look through all of the records in order to find the short URL, we go to memory, we look at this index, and we ask it, hey, where is short URL 123? And it's going to tell us where in disk it is, and we can just seek to disk, or we can just go exactly to that place in disk, find the long URL, and return it. It makes it much, much faster. Now, when you add a primary key to something like Postgres, and let's say that our database here was Postgres, then it uses a B tree as the index. A B tree is like it is a self-balancing tree, it is a self-balancing tree. And if you've been studying for your coding interviews, you know plenty about trees. And so it's going to make this log n. Oftentimes actually much quicker than that. There are quite a few optimizations that exist in modern databases nowadays. But that's what's going to happen, and it's going to make this lookup a lot faster. Now you do have an option of additionally creating a further index, basically a second index on this short URL, which can be a hash index. And this would be O of 1. It would hash the short URL and then point directly to where the row is for us to get the long URL. You could totally do this. Realistically, you don't need to. These B trees in Postgres, for example, and all of these modern databases are so well optimized for these like equivalency lookups that it would effectively be the same. So not something to actually worry about. Now, we're still going to disk. Like we solved one part. We don't have to go to disk and then read all the records in disk. We're going to go to memory. We're going to use that index to find where we need to go in disk, but we still need to go to disk and then back. Realistically, SSDs are really fast nowadays. So this wouldn't probably be a problem. But we could certainly make it faster by never having to go to disk in the first place and only ever going to memory. And so while we're going to index first, that was our first option. We added that here, index. Our second option is that we're going to add a cache. And so we can use something like Redis. We could use memcached. We can use any in-memory cache here. And what this cache is it's just another server. It's just another computer somewhere, a separate instance, a separate computer running. And we're just going to utilize its memory. We're going to utilize its RAM in order to be really quick here. And so we're going to make this be a read-through, least recently used. So read through, least recently used cache. What the heck does that mean, right? It means that any time that we want a short URL, or we want a long URL for a short URL, we're going to look in the cache. And if there's a cache miss, then we're going to get it from the database, update our cache, and then return it. That's the read-through nature. The least recently used is just saying if this cache gets full, then our eviction policy is that anything that hasn't been touched lately, kick it. Because the reality of a system like a URL shortener is that there are going to be some URLs that are really hot, that are getting called all the time. But after a couple weeks, months, no one's going to use the old URLs anymore. And so there's no reason for us to have them cached. Their lookup might take a little bit longer the first time. Who cares? And so caches like this are oftentimes just key value pairs. That's at least most common. That's why I say oftentimes. And so in our case, the key is just going to be that short code or that short URL. And then the value is just going to be the long URL. And so it's going to be a really quick in-memory O of 1 lookup if we have a hit. If we have a miss, then we have to come to our database, look it up by the index, place it in the cache, and then return it. But the subsequent call will be O of 1 again. So that's what we can do there. Great option. Now there is one thing that we could do further. I would actually stop here and argue that this is best for some of the reasons, the arguments that I made when it pertained to the 302 versus 301. But we could also cache in a CDN, a content delivery network. What these are is like they're little edge servers that are geographically located all over the world. So you can imagine that our primary service maybe is sitting there in California, and you're trying to request a short URL from China. Well, there's a lot of latency required in making that request all the way from China over to California. And so CDNs are these servers that are all over the world. And the user then would hit that server in China, and we would have cached on that CDN any responses to any of our, for example, API requests to redirect to a longer URL from a short URL. There it is, right? So we could do that. But the problem is it's going to hit that CDN and then just redirect the user, and it's never going to come to our primary server. So there's the same issues we mentioned with the 302, 301 redirect, which is that in the case of a 301 redirect, it's a permanent redirect, so it never hits our primary server, and we don't know if our service is, working. And so if we care about knowing if our service is working and logging and analytics, then we wouldn't use a CDN. If we don't care about that, then we could use a CDN, but we could also use a 301 redirect, and then we'll just have less things come to our primary server, and we have more caching at the edge, both the user's browsers, DNSs, and CDN respectively. So good discussion to have with your interview. This is kind of the essence of these system design interviews. There's no right or wrong answer. It's trade-offs, it's discussions, it's weighing different priorities. And so something important to note. Heading back over to our non-functional requirements, we can head to our next one, which is scale to support 100 million daily active users and 1 billion URLs. And so when we talk about scale, we want to work our way typically left to right of our system and see where all the bottlenecks would be. All of our services here, all of our components, how do they need to scale? So I'm going to move some things around a little bit just so that we have room. But the first thing that we're going to look at here is our primary server. And so does our primary server even need to scale? Well, we said that we had 100 million daily active users. Now let's just say that each one of those daily active users does one redirect. This seems normal. Maybe it could be 2, maybe it could be 3, change your estimate, but I'm going to say that the average is about 1 redirect. And so 100 million is the same as 10 to the 8th. When you're doing math in a system design interview, I suggest you use exponents like this because it makes the math a lot easier. Watch this. So we have 10 to the 8th, and then there's 100,000 on average, not on average, but rounded up, seconds in a day, right? So that's 10 to the 5. And so 10 to the 8 divided by 10 to the 5 is just subtraction on the exponents. So 10 to the 3. In other words, 1,000. So we have 1,000 requests per second, okay? That's if it's evenly distributed. But we want to handle some peaks, so maybe we multiply by 10, or maybe we multiply by 100. In either case, we're somewhere between 10 to 100K requests per second being our peak here. So we did that math pretty quickly. It's kind of a handy tool using the exponents in that way. And so then you start to build up some intuition about what is a lot. And so an EC2 average instance, like a T3 medium, can handle around 1,000 requests at a time. I say around, this is intentionally hand-wavy. Like this depends on A, how computationally expensive these requests are, how much memory is being used, how much CPU is being used, how large the payloads are, how much bandwidth is being used. Like these numbers are very rough, but in an interview you can use that roughly. Like 1,000 requests concurrently is reasonable enough. And so we can't handle this in one instance here. If this was just one server and it could handle 1,000 requests per second and we have 10K or 100K, we obviously need to do something different here. And so we have two options to us. You probably read about these. The first is what we call vertically scaling. And this is just making this box bigger. So like box plus basically. And when I say box, of course, this is the server. It's just some terminology there. And so we can go to a bigger instance. Instead of a T3 medium, we can pump it up to something that has more CPU, more memory, can handle more bandwidth, like a bigger box. That's one option. It's more expensive. Another option, and this one's the most common one, certainly in system design interviews, is that we scale horizontally. And that means that we just have more of these, and that each request that comes in goes to one of them, right? And so that's a really good option, and the option that we're going to take here. We're going to scale this horizontally. But one thing that's interesting to note is that there are a lot of reads in our system, 100K writes per second for that redirect. But this get short URL, we could imagine that there's far fewer of those. Like, there are very few people who are trying to actually create a short URL every day. Maybe it's 1,000th of the amount of people here. So just like one request per second. It's not a lot. And so that doesn't need to scale a lot. The reads need to scale a lot. And so as a result, what we can do here is something kind of interesting, which is that we can evolve our design to be a microservice architecture. And in doing so, we're going to have two separate services, both of which are scaling horizontally. We're going to have one here, which is our read service. This one's going to be responsible for the redirection. And one which is our write service. This one's going to be responsible for creating the short URLs. And then in doing so, we're going to introduce a new component here that we call an API gateway. And it's responsible for being the entry point. So the API gateway gets a request for one of those API endpoints that we define. And then it's going to determine, based on that API endpoint, which one of these services do I go to? Which one should I route this request to? The read service or the write service, respectively. And then the write service, of course, we're going to do this. Let's just tie everything together here. We have this is only on the read service. And then this still goes through here. Or maybe you can make this abstraction like this if you want to, since it's a read through, but in any case, kind of the same thing, just a little bit of a layer of abstraction there. Okay, and so now we've split this up, and what this means is that this read service, we're going to scale this one horizontally. We're going to have a lot of them, bang, 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 and we might have far fewer of these write services, and it affords us the ability to do so. Now, let me just note that this is true, and it would be a good thing to say in your system design interview. But there's like a very little bit of code happening on both of these boxes. And the reality is, like, splitting this up into two means that you have two different services to maintain, and it's probably overkill. There's no right or wrong answer, but I just want to call that out. You very well could just keep these in the same box and scale them the same. But, it's a trade-off to weigh. This is totally a valid option too. So feel free to discuss it in your interview. Now, with each of these services, when it comes to their scaling, nowadays, this is like all handled for you on the modern cloud infrastructure, whether it's Google Cloud or AWS or Azure or otherwise, and there's just auto scaling. And so you can have these EC2 instances or in the AWS world, and you configure memory in CPU limits. So you basically say if 75% of my cluster's memory is used, or if 75% of my CPUs are used, throw up a new box. And then if less than 20% is being used, take a box down. And these things will just scale automatically. And yes, technically, of course, there's a load balancer here in front of them that is taking these requests and then just routing them either with round robin or however else you configure it within your cloud dashboard. And it's routing it to each of the boxes. But that's how it works in practice nowadays. Like, you don't actually control the up and down. It's just all auto scaling. So that's something that's worthwhile to know. Okay, so that's how we scaled our services. Now with that write service though, we have an issue. Remember we had that global counter here, or we had that counter here. Now this counter, if we have multiple of these write services, we can't have two different counters. They're not in sync. Like, they both start at 0 and then they go to 1, and now there's two 1s, there's two 2s. You get the picture, right? So this isn't gonna work. And instead we need all of these write services to agree on the same current count. And so what we need to do is we need to pull this counter off of the instances. Basically, that counter can't be in memory anymore on these particular servers. We need what we can call like a global counter. And so we can have a global counter here. And this global counter, again, could be Redis. For what it's worth, it could be the same instance too. I'm just drawing this separately to make it easy to see. And now they're both going to ask this global counter for what's the next count. And it just keeps a single count here that goes from 1 to 2 to 3. You get the picture all the way up, right? And so in Redis's world, Redis has an incr which is a command that's just going to increment a counter. You can have that counter here in memory. And because Redis is single-threaded, you don't have to worry about any concurrency. It's single-threaded, so we're going to do one incur at a time, and it's wicked fast because it's in memory, and then we're just going to do the next one. So the count is always increasing. Now, one thing I'll mention just quickly is that this means now that in order to get the count, you got to go somewhere else, make a network call, get the count, come back, do your calculation, send it to the database. You added a step here. And so one thing that we could do, which is kind of cute, is that when a server comes online, we can request like the next 1,000 counts, for example, and then keep all of those in our internal memory, and then just be using those until we need to request the next 1,000 counts. And if this server goes down before we used all 1,000, no big deal. Like those are lost forever, those counts, but it's fine, right? We had up until what it was like 3.5 trillion until we needed to add the seventh character there. So we can afford to lose some, there's no big deal. But this is how this would work. I'm gonna remove that and you guys can just remember that these are both horizontally scaled respectively. Okay, and then what about the database? So let's head over this way now. How does this guy need to scale? Well, again, let's do a little bit of math here. Maybe I'll do it right here. So we have a short code, that's like 8 bytes. We have a long URL, maybe that's like 100 bytes. We have a creation time, those are always 8 bytes. We have an optional custom alias, maybe that's up to 100 bytes. That'd be crazy though, because it should be small, so that's on the high end. An expiration time, 8 bytes. You know, this is 216 bytes, 232 bytes. Let's just round up because maybe we want to throw more stuff in there. Let's say 500 bytes. And so we have 500 bytes times 1 billion rows. And so that ends up just being 500 gigabytes. 500 gigabytes isn't a lot. Modern SSDs are in like the hundreds of terabytes. Like 500 gigabytes is nothing. So we can just have a single instance of our database. It's no big deal. The only other thing we'd be concerned about is the read throughput. Like, can our database handle the read throughput? And we put most of the reads on Redis anyway in our cache. So our database is chilling. It's good to go. Now, if we did need to scale the database, then we would shard probably by our short URL. And that would mean that we would just have multiple instances of our database. And where the data was stored would be based on like, take your short URL modulo 3 and store it on one of those databases. That's kind of how that works. But in this case, we didn't need to. We did the math and we proved that it doesn't matter. And so at this point, our system is fully scaled. Coming back over, the last thing that we had was high availability. Now, most of what we've done by having the auto scaling, by separating these and scaling them independently, horizontal scaling, we're at this point largely available. There are some things that we want to consider, like Redis here. We would want to make sure that we probably have, honestly, I don't care. Actually, if Redis goes down, it's fine because it's read through, so we'll load it back up by just hitting the database. We'll be slow for a little bit, no big deal. If the global counter goes down, that would be a problem. So we'd want to have some high availability modes here, which basically means that we would have some redundancy. We can also periodically snapshot the count and save it to disk. If you want to look up Redis high availability mode, it'll explain to you more about how all of that works. But that's a configuration here. In the database too, we can have some replicas. So maybe we have a single replica. We frankly probably don't even, I don't know, having a single replica would be good in case the database went down. But we're also just going to take snapshots every hour or so. So a snapshot of the current state of the database stored in something like S3, a big cheap blob storage. And that way if the database ever goes down, we just pull it back up. Having that replica there means that if one database goes down, we can just point to the replica and it can be in charge for a while until we get our snapshot back up. But that should satisfy our high availability in this case, no problem. So at this point, we take a look back at our requirements and we've satisfied all of our functional requirements when we did the high level design. We've now satisfied all of our non-functional requirements. And we look at ourselves and we say, I nailed it. Like, I've passed this interview. I've crushed it and I know I've crushed it because me and my interviewer agreed on the requirements and I have now completed my design satisfying all of those requirements. And so I'm feeling really good. You should be feeling really good. Hopefully you learned a lot as well. So there you have it. I hope you all learned something today, especially if you're new to system design. I really hope you found this useful. We're going to get back to our regularly scheduled programming, don't worry, with some of those more complex problems and breakdowns coming out in the near future. As always, if you have questions, feedbacks, things that you think I did wrong, please go ahead and leave a comment. I'd love to hear from you, and I get to as many of those as I can, so don't hesitate there. And of course, don't forget to like and subscribe. All right, good luck in your upcoming interviews. I'll see y'all soon.